Hello friends, welcome to my lecture on complex integration. Why do we study complex integration? The integration in the complex plane is important because there are many real integrals which can be evaluated by complex integration, while the usual methods of real integral calculus fail in those cases. So, and further in the complex integration we are able to prove some basic properties of analytic functions, like the existence of higher order derivatives, which will be otherwise difficult to establish. Let us consider first the line integral in the complex plane. So, let us consider the parametric representation of a curve C in the complex z plane. Let z t equal to x t plus I y t, a less than or equal to t less than or equal to b be the parametric form of a curve C in the complex z plane. Let us assume that the curve C is smooth, that is the z t function is continuously differentiable for all t belonging to the closed interval a b, and dz by dt is not equal to 0. Z dot t means dz by dt is not equal to 0. The length of the curve, we know the length of the curve S is then given by S equal to integral a to b dx by dt whole square plus dy by dt whole square dt. The curve C is then called the rectifiable curve. Now, the positive direction along C corresponds to the sense of increasing values of t. The direction in which the values of t increase, okay, is said to be the positive sense along the curve C. Let us consider a continuous function f z at each point of C. Let us say f z is a continuous function at each point of C. We subdivide the interval a b, okay, the interval closed interval a b by means of these n plus 1 points, t naught equal to a, t 1, t 2, t n minus 1 and t n equal to b. Okay. So, this is your suppose interval a b, let us divide it into n parts. Okay. So, t naught is less than t 1, less than t 2, less than t n minus 1, less than t n. Now, we have z t equal to x t plus I y t, where a is less than or equal to t, less than or equal to b. So, corresponding to these values of t, t naught, t 1, t 2, t 3, t n minus 1, t n, there will be the values of z. Okay. So, let us say z t I equal to z I, where I varies from I goes from 0 to n. Okay. So, that means z t naught equal to z naught, z t 1 equal to z 1 and z t n equal to z n. Then these curves, this curve, let us say this is curve C, okay, z naught is the point here, z 1 is the point here, z 2 here, and this is your z is there, this is z n. Okay. Now, on each portion of a subdivision, so this divides the curve into n parts. On each portion of a subdivision of C, let us choose a point, say zeta 1 between z naught and z 1. So, here we choose zeta 1, between z 1 and z 2 we choose a point zeta 2, and so on between z 1 z m minus 1 and z m we choose a point zeta m in a completely arbitrary manner, and so on. So, and then we form a sum, okay, S n. So, S n will be sigma m equal to, because in the nth interval z n minus 1 z n minus 1 z n we choose zeta n. Okay. So, then and since f is a continuous function at each point of C, so we can find the values of f at zeta 1, zeta 2, zeta m and zeta n, and then multiply them by delta z m. Delta f zeta m is multiplied by delta z m, where delta z m is z m minus 1. Okay. This is your z m minus 1, this is z m, and the magnitude of delta z m, mod of delta z m, this is the distance between z m and z m minus 1. Okay. So, the length of this chord, okay, mod of delta z m is the length of this chord. So, you multiply f zeta m by delta zm and form the sum from over sigma over m from 1 to n. So, Sn you get sigma m equal to 1 to n f zeta m delta zm, and this we do for each value of n equal to 2, 3 and so on. We have divided into n parts. So, let us start with n equal to 2. We divide first into 2 parts, okay, form Sn means form we get S2, okay, for n equal to 2 we get S2, for n equal to 3 similarly we get S3 and so on. Okay. So, this we do in a completely independent manner, but in such a way that when you subdivide the curve C into n parts, let us let n go and increase and go to infinity, we do this in such a way that the maximum of mod of delta Zm, maximum of mod of delta Zm, okay, goes to 0 as n goes to infinity. That is means the maximum arc length, maximum chord length, okay, delta Z mod of delta Zm is the distance between Zm and Zm minus 1, okay. Maximum of mod of delta Zm tends to 0 as n goes to infinity. Then the sequence of complex number S2, S3 and so on, that converges to the integral of Fz along C, okay, the limit of the sequence as n goes to infinity, and it is called the line integral of Fz along the oriented curve C. We are considering an orientation of the curve C, okay. We have decided taken a sense along the curve C, okay. So, it is called an oriented curve. So, oriented curve C, and we denote it by integral over C Fz dz. The curve C is called the path of the integration. So, integral over C Fz dz here is the limit of Sn as n goes to infinity, but in such a way that maximum of mod of delta Zm, okay, 1 less than or equal to m less than or equal to m goes to 0. Okay. So, this is how we the definition of the line integral of Fz, okay, is exactly same as we do it in the case of real integrals. So, now let us discuss the existence of the complex line integral. Fz is a complex function. So, let us take the real and imaginary parts of Fz as uxy and vxy. So, Fz is uxy plus ivxy. Let us zeta m is a point which lies between Zm minus 1 and Zm. So, we can take it as xm plus I eta m, and delta Zm z is x plus iy. So, delta z is delta x plus I delta y. So, delta Zm which is the Zm minus 1, Zm is delta Zm is Zm minus 1. Okay. So, delta Zm, because of delta Z being delta x plus I delta y, we write delta Zm as delta xm plus I delta by m. Okay. If Zm is say xm plus I ym and Zm minus 1 is xm minus 1 plus im minus 1, then I ym minus 1. So, then we can get delta xm delta ym. So, delta z is delta xm plus I delta ym. Then the equation 1 yields, we get the following equation 1, okay. This equation Sn equal to, we have Sn equal to sigma m equal to 1 to n f zeta m delta Zm, okay. This gives you sigma m equal to 1 to n, f zeta m will give you xi m eta m, because this zeta m is xi m plus I eta m, its real part is xi m, imaginary part is eta m. So, we get u xi m eta m plus I v xi m eta m, this multiplied by delta Zm, which is delta xm plus I delta ym. Okay. So, we multiply this expression by delta xm plus I delta ym and sum over m equal to 1 to n. Then if you multiply these two factors, this factor and this expression and this expression, what you get is this, and use iota square equal to minus 1. Okay. We get sigma m equal to 1 to n, use I m eta m delta x m minus sigma m equal to 1 to n, b is I m eta m delta y m plus iota times sigma m equal to 1 to n, use I m eta m delta y m plus m equal to 1 to n, b is I m eta m delta x m. Now, all these sums, okay, all these sums are real. You can see u x by is a real function, delta x is also real. So, u x by into delta x is a real quantity. So, these all these expressions this and this, they are all real sums. Okay. Since f is a continuous function, so its real and imaginary parts are continuous, u x y and b x y are continuous functions, and therefore, as n goes to infinity, when maximum of mod of delta z m goes to 0, maximum of mod of delta x m and mod of delta y m also goes to 0. You can see we have delta z m equal to this. Okay. So, delta z m goes to 0, mod of delta z m will be what? Under root delta x m square delta by m square. Okay. So, when maximum of mod of delta z m goes to 0, when this goes to 0, okay, delta x m and delta y m, they will also tend to 0. Okay. So, they will also approach 0, and hence each sum here can be replaced by a real integral. So, limit n tends to infinity S n gives you integral over c f z d z, which is equal to integral over c u x by d x minus integral over c b x by dy plus iota times integral over c u x by dy, because we have delta y here, delta y m. So, we get u x by dy plus integral over b x by integral over c b x y. Okay. So, the evaluation of a complex function, okay, a complex integral reduces to evaluation of 4 real integrals, this integral, this integral, this integral and this integral. Now, and evaluation of these real integrals, these 4 integrals, this one, this one, this one and this one, can be done easily by using the parametric form of the curve C. Okay. So, we replace integral over C u dx by integral over C u dx over dt dt. So, integral over C u x by dx will be written as integral over a to b u x t by t dx over dt dt. Okay. And we know that as the parametric form of the curve C is z t equal to x t plus I by t, where a is less than or equal to t less than or equal to b. So, this is how we can evaluate the integral of u with respect to x, integral of b we can find with respect to y and so on. Okay. So, these 4 real integrals can be determined and we get the integral over c f z d z. Now, briefly this can be expressed further in a simpler form. You can write, actually this is nothing but integral over a to b f z t dot z, this is z dot t dt, z dot t is dz by dt. Okay. And dz by dt is dx by dt plus I dy by dt. Okay. As you can see in f z t, f z is equal to u x by plus I b x by. So, f of z t will be equal to u x t y t plus iota v x t y t. Okay. So, when you multiply f z t, okay, by z dot t, okay, and use iota square equal to minus 1, okay, and integrate over a to b, what you get is the expressions this one, okay. This is nothing but this quantity, this is nothing but integral over a to b u x t by t plus I b x t by t into d over dt of x t plus I by t dt. Okay. If you multiply these two, you get this right hand side. So, this is, and this is nothing but integral over a to b f z t into z dot t dt. So, integral over c f z dz by using the parametric form of the complex of the curve C can be the complex integration can be replaced by the definite integration. So, we get this. Now, let us first, for example, consider integral over C 1 over z minus z naught dz, where C is the circle of radius a and center z naught in the counterclockwise. So, we are moving along the curve C in the counterclockwise direction. Okay. What we do is, let us write the parametric form of the curve C. We can write the equation of the curve C is what? Mod of z minus z naught equal to a. Okay. Because if a is the radius and z naught is the center, we know that the curve C can be written as mod of z minus z naught equal to a. So, we write in the parametric form, we write it as z minus z naught equal to a times e to the power I t. Okay. And we are moving in the counterclockwise direction. So, we have 0 less than or equal to t less than or equal to 2 pi. Okay. So, you can see here we have the figure here, you can see this is your figure. Okay. We are moving, the center is at z naught, radius is a. If you take the point P here, theta, since I have written z minus z naught equal to a e raised to the power I t, this theta is equal to t for us. Okay. So, you can see t is 0 here. Okay. Here theta t is 0 and it moves from 0 to 2 pi when we go in the counterclockwise direction. Okay. So, integral over C f z dz we have seen this is equal to integral over a to b f z t dz by dt into dt. Okay. So, replacing z by z t in the equation of the function f z, we will get f z t. F z is given as 1 over z minus z naught here. Okay. The complex form of the function f z is 1 over z minus z naught. So, let us use the parametric form. So, when you use the parametric form, f z becomes f z t and f z t will be equal to integral limits are 0 to 2 pi. 0 to 2 pi. Okay. F z t will be 1 over a e raised to the power iota t. Okay. Z minus z naught is a e raised to power iota t, and dz by dt, let us find z minus z naught equal to a e to the power I t. When we differentiate with respect to t, dz by dt, z naught is a constant. So, its derivative with respect to t is 0. So, we get a e to the power I t into I. Okay. So, we put the value here a e to the power I t into I dt. Now, e to the power I t is never 0. So, we can cancel out and what we get is I times integral 0 to 2 pi dt. So, we get 2 pi into iota. This is how we get the value of the given integral using the parametric form of the complex parametric form of the curve C. Let us take another problem, f z equal to mod of z. Okay. So, we have to integrate f z along the semicircle ABD here. You can see this semicircle ABD. Okay. ABD. Okay. This semicircle ABD. So, we have to integrate along the semicircle ABD and its center is at origin, okay. Radius we can take to be r, okay. So, we have to integrate f z along the semicircle ABD, and then in the second case we have to integrate along the semicircle BCA. So, semicircle BCA is this one, okay, this is semicircle BCA. So, first we integrate along ABD, okay. So, let us see, we have f z equal to mod of z. So, we have to integrate f z dz a dB, okay. So, what we will do is f z equal to mod of z. So, integral a dB mod of z dz we have to find, okay. So, let us write z equal to, let z be equal to r e to the power I theta, r e to the power I theta. So, then mod of z is equal to r, okay. Now, you can see here theta varies from, theta is equal to minus pi by 2 here, and theta is equal to pi by 2 here. So, when you integrate mod of z along a dB, what you get, integral over, we can write z equal to r e I theta, and theta varies from minus pi by 2 to pi by 2 in case of a dB. For a dB, z is equal to r e I theta, where theta varies from minus pi by 2 to pi by 2. So, minus pi by 2 to pi by 2, and mod of z is equal to r. So, we get r times, and then dz by d theta into d theta, because f z is integral over limits of theta, say alpha to beta, f z theta dz by d theta into d theta, okay, by our article on complex line integral. So, this will be how much? This is dz by d theta will be equal to r e to the power I theta into I d theta, okay. So, this is minus pi by 2 to pi by 2 r times r e to the power I theta into I d theta. R square we can write outside, I also we can write outside. So, minus pi by 2 to pi by 2 e to the power I theta d theta, okay. Now, so then integral over a dB f z dz is equal to I r square this is what we get, okay. So, now e to the power I theta, we know it is cos theta plus I sin theta, okay. So, e to the power I pi by 2 is cos pi by 2 plus I sin pi by 2, and this is equal to, cos pi by 2 is 0, sin pi by 2 is 1. So, we get iota here, and similarly e to the power minus I pi by 2 is equal to cos pi by 2 minus I sin pi by 2. So, this is minus I. So, what do we get here? R square times I minus minus I, and we get 2 I r square. So, in the particular case, r equal to 1, okay, we get the value 2 I, okay. Mod of z equal to r we have taken. So, mod of z equal to 1 here, okay. Mod of z equal to 1 is called the unit circle. So, if you consider the unit circle, I mean to say that integral of mod of z along ADB is equal to 2I. Now, let us consider the case of BCA. Okay, so, BCA is this. Okay. So, here when you move in this direction, theta increases from 0 to pi by 2, then to pi, and then 3 pi by 2. Okay. So, now we shall integrate along when you move along BCA, okay, then you what you will get is this. We start with theta equal to pi by 2 and go up to theta equal to 3 pi by 2. Okay. F z theta will be equal to mod of z is equal to r. So, r and dz by theta d theta we have already found r e to the power I theta into I d theta. Okay. So, what we get is I times r square pi by 2 to 3 pi by 2 e to the power I theta d theta. Okay. So, this will give you this one, okay, integral over BCA f z dz equal to I r square and this is equal to r square times so this I cancels with this I and what we get r square times e to the power 3 I pi by 2 minus e to the power I pi by 2 e to the power 3 I pi by 2 is equal to cos 3 pi by 2 plus I sin 3 pi by 2. We know that cos 3 pi by 2 is 0 and sin 3 pi by 2 is sin pi plus pi by 2. So, minus sin pi by 2. So, we get I times minus 1. So, this is minus I. So, this is equal to r square times minus I and e to the power I pi by 2 is cos pi by 2 plus I sin pi by 2. So, again I. So, we get minus I. So, we get minus 2 I r square. Okay. And thus, in the particular case r equal to 1, okay, we get minus 2I. Okay. So, when you integrate along the semicircle VCA where the circle has radius 1, you get the value minus 2I. Okay, let us consider one more example f z equal to real part of z. Okay. So, let z be equal to x plus I y. So, then real part of z is equal to x and hence f z is equal to real part of z means x. Okay. We are considering the line segment from z equal to 0 to z equal to 1 plus I. So, this is z equal to 0 origin, here z is equal to 0 and z equal to 1 plus I means one point. Okay. So, one point. Oh, this is x equal to 1 and this is y equal to 1. Okay. So, 1 point. We are going from 0 to 1 plus I direct. Okay. So, this is the line segment where we are integrating and we are integrating from z equal to 0 to z equal to 1 plus I. This is nothing but equivalent to z equal to 1 plus I. Okay. So, integral over C f z dz here will be equal to okay, f z is x dz. Okay. Now, what do we do? Z is equal to x plus I y. Okay. So, we can write here dz is equal to z is equal to x plus I y. So, dz is equal to dx plus I dy. So, I can write it as integral over c x dx plus I dy. Okay. The equation of the line, okay, line joining zero zero to 1 1 is given by equal to x. Okay. So, dy equal to dx. Okay. So, I can write integral over x and then dx plus I dx, that is 1 plus I dx. Okay. And x varies from 0 to 1. Okay. So, 0 less than or equal to x less than or equal to 1. Okay. Line segment joining 0 0 to 1 1 is given by equal to x, where 0 less than or equal to x less than or equal to 1. So, 0 to 1. So, we get 1 plus I is a constant, we can write it outside, and 0 to 1 x dx we get. So, this is 1 plus I times x square by 2 0 1. Okay. So, 1 plus I times 1 over 2. So, I can write 1 plus I over 2. Here what I have done is parametric form of the curve C I have taken, where in place of t I have written x. Okay. So, actually I am considering the parameter t to be equal to x here. So, x here we have taken as t, or you can and y is also equal to t. Okay. So, this same as the complex integration, we have taken the, instead of the parameter t we have taken x, and y is equal to x. So, y is also equal to t. So, this is what we get when we integrate from z equal to 0 to z equal to 1 plus I along the line segment. Now, in this second case we integrate along this one. This is your z equal to 0, this z equal to 1 0 point, and this is your 1 1 point, okay, which is same as z equal to 1 plus I. Okay. So, we have to move along the real axis, this is real axis. Okay. We have to move along the real axis from 0 to z equal to 0 to z equal to 1, this is z equal to 0, this is z equal to 1, and then vertically to 1 plus I. From z equal to 1 to z equal to 1 plus I, we are moving vertically. Okay. So, integral over C f z dz is equal to integral over, let us say this is I can write it as some let us say A point and this is B point. So, integral over OA plus integral over OB f z dz. Okay. So, integral over OA f z dz but now when we go from O to A, okay, along the real axis, along OA y is equal to 0. Okay. So, z is equal to x. Z equal to x means f z is real part of z, real part of z is x. So, x times dz equal to dx, and x varies from 0 to 1. Okay. So, 0 to 1 x dx we have. Now, along O this is AB, this is AB, we are going from O to A, then A to B. Okay. So, AB means now along AB what is happening is x is equal to constant, x is equal to 1, okay, and x is equal to 1 and y varies from 0 to 1. Okay. So, when x is equal to 1, dx dx equal to dx equal to 0. So, dz equal to I dy. Okay. So, we will have here x times I dy and by varies from 0 to 1. Okay. So, we get here x is equal to 1, we will put there. Okay. So, we will get here x square by 2 0 to 1 and then iota times x is equal to 1 along AB. So, we have here iota dy as x equal to 1 along AB. Okay. So, what you get here? So, we get here 1 by 2 and then we had I times, so we get 1 by 2 plus I. Now, you can see here the value that we obtained by integrating along the line segment from z equal to 0 to z equal to 1 plus I, that was 1 plus I by 2, while the value that we got from by integrating from 0 to a and then a to b is 1 by 2 plus I. So, both the values are not same. Okay. And therefore, the value of the integral does not always depend on the endpoints, it also depends on the geometric shape of the path. So, we shall see later on, because this function f z equal to real z, it is not analytic. Okay. So, that is why such a thing has happened. Whenever a function f z is analytic, okay, along whatever in the region of the analyticity of f z, along whatever path you integrate from say z1 to z2, the value of the integral does not depend on the geometric shape of the path, it remains the constant. It only depends on the points z1 and z2, not on the geometric shape of the path, but the function f z is equal to real z here actually is not analytic. So, such a thing has happened. Now, let us consider another example, integral over c f z dz, where f z is equal to z square plus 3 z to the power minus 4, where c is upper half of the unit circle from z equal to from 1 0 to minus 1 0. Let us draw the curve first. So, this is your unit circle, mod of z equal to 1, the center is 0 and radius is 1. Okay. We are considering c is the upper half of the unit circle from 1 0, this is 1 0 point. So, 1 0 to g minus 1 0. So, we have to integrate f z along the upper half. So, this is parametric. So, c is mod z equal to 1, the parametric form is z equal to e to the power I theta, and theta varies here from theta is 0 here at 1 0 and at minus 1 0 theta is pi. Okay. So, theta varies from 0 to pi, this is our curve C. Okay. So, integral over C f z dz is equal to integral over 0 to pi f z, when z is replaced by z theta, is e to the power I theta. So, e to the power I theta whole square plus 3 times e to the power minus 4 I theta, and dz replaced by dz by d theta, dz by d theta is e to the power I theta into I. So, this is e to the power I theta into I d theta. So, what we get here then, 0 to pi e raised to the power I theta whole square is e to the power 2 I theta into e to the power I theta, I can this I can write outside. So, e to the power I theta into e to the power 2 I theta is e to the power 3 I theta, okay, plus 3 times e to the power minus 3 I theta d theta. Now, this is equal to I times e to the power 3 I theta over 3 I, 3 times e to the power minus 3 I theta divided by minus 3 I 0 pi. Okay. So, this I can cancel with these i's and I get e to the power 3 I. Okay. So, what I get 1 over 3 I can write outside. Okay. This 3 and this 3. So, e to the power 3 I pi plus 3 times, so minus, okay, minus 3 e to the power minus 3 I pi, okay, and then we put the lower limit. So, minus e to the power 0, that is 1, and then we get plus 3 e to the power 0, that is 1. Okay. So, e to the power 3 I pi, e to the power 3 I pi is equal to cos 3 pi plus I sin 3 pi. Cos 3 pi is cos 2 pi plus pi, which is cos pi. So, cos pi is minus 1 and sin 3 pi is 0. So, I get minus 1 here. E to the power minus 3 I pi will be equal to cos 3 pi minus I sin 3 pi, and this is also equal to minus 1. So, what I get 1 by 3. So, I get here minus 1, then here I get 3 here, then a minus 1 plus 3. So, this is 4 by 3. So, this is the value of the line integral of f z along f z equal to z square plus 3 times z to the power minus 4 along the unit circle from the point 1 0 to the point minus 1 0. That is all in this lecture. Thank you very much for your attention.